Welcome back to the Deep Dive, where we dig into complex source material and really turn it into actionable knowledge for you.
Yep.
And today, we have a fantastic set of sources, all centered on what I'd call the engine room of modern C++ Tendo. We're talking about the Standard Template Library, the STL.
Absolutely fundamental stuff.
And our mission for this deep dive is to go way beyond just definitions. We want to get into the architecture and specifically zero in on the STL containers. The goal is to give you a really practical feel for the choices you have to make.
Because that choice matters a lot. Making the wrong one early on can, cost you weeks of work down the line trying to optimize.
So true. So for anyone just jumping in, what is the STL at its core?
Well, at a high level, it's this incredibly powerful, standardized set of template classes. It gives you all these pre-tested, high-performance versions of common data structures and algorithms.
Things like vectors, lists, maps.
Exactly, all the things you'd otherwise have to write yourself. It's really the framework that C++'s reputation for efficiency is built on.
And that idea, that efficiency and reusability is so important. Let's just quickly nail down the main benefits the sources point to. Why do we even use it?
Right. Well, number one is reusability. I mean, why would you write your own sorting algorithm when the one in the STL is guaranteed to be correct and it's maintained by, the entire C++ community? It just speeds things up massively.
And it's probably faster than anything I'd write myself.
That's the second point, efficiency. These implementations are they're rigorously optimized. They're often pushed to the absolute theoretical limits for the hardware. You get that speed right out of the box.
Okay, and the third one, which I think is the real magic of C++ and the STL, is the flexibility.
Precisely. It's all built on templates, which means the whole library is generic. It doesn't care if you're storing integers or some, super complex custom object you just made.
The container just adapts to your data type.
Yep, it just works.
Okay, so we've got this fast, flexible, pre-tested toolkit. But how is it all organized? Let's talk about that foundational architecture, the four pillars.
The sources break it down really elegantly into four parts that all work together. First up, you have the containers.
Which we're focusing on today.
Right. These are the actual data structures, the vessels that hold your collections of data.
Okay, so that's pillar one. What's two?
Algorithms. These are the functions that do the work. Sorting, searching, counting, manipulating. They operate on the data inside the containers.
And they're designed to be totally separate from the containers themselves.
Completely agnostic. And that separation is made possible by the third pillar, which is kind of the unsung hero of the whole system.
The iterator.
The iterator, it's this brilliant pointer-like object. It basically gives an algorithm a standard way to walk through a container and access its elements without the algorithm needing to know anything about how that container is built internally.
It's the universal adapter, the glue.
It is absolutely the glue that holds the whole generic programming model together.
Okay, so containers, algorithms, iterators. And the fourth one is for customization.
Function objects, or functors, basically they're objects that you can call, they're functions. They're key for customizing how algorithms behave.
Like if you want to sort in descending order instead of ascending.
Perfect example. You'd pass in a functor that defines that custom less than logic. Or, sort of a list of products by price or by name.
And it's interesting because a lot of modern C++ uses lambdas for that now, which can be a bit cleaner.
For simple cases, yes. But functors are still powerful because as objects, they can hold state. So if you need to keep track of something across multiple calls to an algorithm, a functor is still the way to go.
Right, a non-capturing lambda can't do that.
Exactly.
Okay, so we have the four parts. Containers store, algorithms manipulate, iterators connect, and functors customize. For the rest of this deep dive, we're hitting the storage engine hard. The containers.
Let's do it.
First up are the sequence containers. The key idea here is linear. Everything's in a specific order.
Right, these are your bread and butter containers, but the way they're built under the hood makes a huge difference in performance.
So, the one everyone knows and loves. The vector.
The vector. It's your default choice for a reason. It's basically a dynamic array, which means all its elements are stored one after the other in a contiguous block of memory.
And that contiguous memory is the secret sauce.
It is. It gives you lightning-fast random access. Getting the millionth element takes the exact same time as getting the first one. It's an O of 1 operation. Plus, CPUs love it because of cache locality.
But its greatest strength is also its biggest weakness. What happens when you run out of space?
Ah, yeah, the reallocation problem. The vector has to go find a new, bigger block of memory, copy every single element over, and then delete the old block.
Which can be a really expensive operation.
It can be, and it's also why inserting or deleting anywhere but the very end is so slow. It's an
Yeah.
O of N operation because you have to shift all the subsequent elements down.
Which brings us to its less flexible cousin, the std.array. Why would you ever pick a fixed size array?
Control and performance. The array's size is fixed at compile time, so it's often allocated right on the stack. No dynamic memory allocation, no overhead for resizing. For small, critical data sets where you know the size and you need every last drop of speed, the array is king.
Okay, so vector and array solve the fast access problem. What about that insertion problem? That's where linked lists come in.
Exactly. And you've got two main flavors here. The standard std.list is a doubly linked list. Each element holds a pointer to the one before it and the one after it.
So inserting or deleting is super cheap.
Incredibly cheap. Constant time, O of 1. You just have to rewire a couple of pointers and you're done, no matter where you are in the list.
But the trade-off is huge, right? Memory and access speed.
It is. First, you have the overhead of 2 pointers for every single element you store. But the bigger issue is that the elements are scattered all over memory. There's no contiguous block.
So no random access.
None. If you want to get to the 500th element, you have to start at the beginning and walk through 499 elements to get there. It's an O of N operation.
And if memory is really tight, there's an even more stripped-down version.
Yep, the forward list. It's a singly linked list. It only stores a pointer to the next element, not the previous one. So you save some memory, but the trade-off is you can only move forward through it.
Makes sense? Okay, one more in this group. The one that tries to be the best of both worlds. The deck, the double-ended queue.
The deck is fascinating. It's usually implemented as a collection of fixed-size memory blocks. So it's not one single contiguous array like a vector, but it's not as scattered as a list.
And what does that clever layout get you?
It lets you do fast insertions and deletions at both the front and the back of the sequence. Both are O of 1 operations.
Okay, so that's huge. If you're constantly adding new items to the front of a collection, a vector would be a disaster.
A total performance disaster. You'd be shifting the entire contents every single time. A deck is built for that exact scenario, while still giving you pretty good random access. Much faster than a list, anyway.
All right, that's a great overview of the linear structures. But what if you don't care about the order? What if all you care about is finding things and finding them fast?
Then you move into the world of associative containers. And this is where you have to make a really critical choice.
The choice between the sorted ones and the not-so-sorted ones.
Exactly. You're choosing between predictable, guaranteed performance versus potentially much faster average case performance, but with a risk.
Let's start with the predictable ones, the sorted group, map, and set.
Right. So map, set, multi-map, multi-set. These are almost always implemented as self-balancing binary search trees. Think red-black trees.
And that structure guarantees performance.
It guarantees that your search, insert, and delete operations will always be O of log n.
Which is very, very fast, even for huge data sets. And the other key feature is they're sorted.
Always sorted by the key. A set just stores unique sorted elements. A map stores unique key value pairs sorted by the key. If you ever need to iterate through your data in a sorted order, this is the group you have to use.
And the multi-versions.
They just relax the uniqueness constraint. Multiset lets you store duplicate elements, and multi-map lets you have multiple entries with the same key. Still sorted, still O of log n.
Okay, so that's the safe ordered bet. Now for the speed demons. The unordered associative containers.
The hashed group. This is unordered map, unordered set, and their multi-friends. They throw sorted order completely out the window in the name of pure speed.
And they do that using hash tables.
Yep. You take a key, run it through a hash function, and that function gives you an index of bucket where your data should go.
So the performance gain is?
Potentially massive. On average, lookup, insertion, and deletion are all O of 1, constant time. That is the fastest you could possibly get. For things like frequency counters or simple lookups where order is totally irrelevant, they're often the best choice.
But you said there was a risk. The Achilles heel of any hash table.
Collisions. If your hash function isn't great, or if the data is just unlucky, you can get a lot of different keys that all hash to the same bucket index.
And then what happens?
Then your O of 1 performance just falls apart. In the worst case scenario, the operation can slow all the way down to O of n because you're basically just doing a linear search through all the collided items in that one bucket.
So that's the trade-off. Guaranteed O of log n with sorting, versus a shot at O of 1, but with a worst case of O of n.
That's the core decision you have to make, and it's a huge one.
Okay, that comparison is incredibly useful. You've done sequence containers, we've done associative containers. The last group is a little different. Container adapters.
Yeah, these are interesting because they aren't really new data structures themselves. They're more like wrappers. They take an existing container and just impose a very strict limited interface on it.
I like your analogy from our notes. It's like taking a big open shipping container and then welding on a tiny funnel and a single exit hatch to control how things go in and out.
That's a perfect way to put it. Take the STD dot stack. It enforces LIFO behavior, last in, first out. You can only push things onto the top and pop things off the top. That's it.
You can't access anything in the middle.
Nope. And interestingly, the container it's wrapping underneath is, by default, usually a deck.
A deck, not a vector. Why is that?
Well, a stack only needs fast operations at one end, the top. A deck is great at fast operations at both ends, so it's a really robust choice that doesn't have that potential reallocation penalty a vector might hit when it grows.
Ah, that makes sense. And the queue is similar.
Very similar. The std.q enforces FIFO, first
Yep.
in, first out, like a line at the store. You add to the back and you remove from the front. And again, it's typically backed by a deck because it needs efficient operations at both ends.
Okay, last one, the priority queue.
This one is a bit different. It's an adapter that ensures that whenever you remove an element, you're always getting the one with the highest priority.
Not necessarily the first or last one in.
Exactly. And its underlying container is usually a vector.
Wait, a vector? Why not a list or deck?
Because a priority queue is implemented as a heap, and a heap data structure needs efficient random access to maintain its properties when you add or remove elements. And for random access, nothing beats a vector.
Wow. We've really covered a lot of ground here. From the benefits of the STL and its 4 pillars, all the way through a really detailed breakdown of the 4 different families of containers.
And it all comes back to one core insight. There is no best container.
It's always about the trade-offs.
Always. You have to match the container to the job. Do you need random access.vector? Worried about insertions in the middle? .list. Need guaranteed sorted lookups.map? Are you willing to gamble for that O of 1 speed? Unordered map. Understanding those technical differences is what separates good code from great high-performance C++ code.
So before we sign off, let's tie this back to the other pillars for a second. We talked about iterators and algorithms. We said iterators are what let an algorithm like std.sort work on any container. But not all iterators are created equal. A vector gives you a random access iterator, but a list only gives you a bidirectional iterator.
A key difference.
So that brings us to our final provocative thought for you to chew on. We know an algorithm like std.sort needs to be able to jump to any element instantly. It needs a random access iterator. So what happens if you try to run std.sort on an std.list? Which container's internal structure forces a massive, maybe even hidden performance hit on an otherwise optimized algorithm? And why might the system have to do a whole bunch of extra work behind the scenes, maybe even a full copy of your data, just to make a slow container compatible with a fast algorithm?
Something to think about.
A lot to think about. That is all the time we have for this deep dive. Go forth and choose your containers wisely. We'll catch you on the next one.